Hopefully this video will clear up how intermolecular forces relate to the melting and boiling points of a substance. Think of it this way. All molecules and atoms experience attractive forces within the substance. Now we're talking about pure substances here, compounds and elements, not mixtures. And these attractions are called intermolecular forces. All molecules have them. All atoms have them. They all experience intermolecular forces. And it is because of these intermolecular forces that we have differences in melting and boiling points. So if you take a solid, those particles, molecules or atoms, whatever it is, are attracted to each other, keeping them in that tight configuration of a solid. But if you give this enough energy to overcome some of that intermolecular force where they are able to flow past each other freely, then we've reached the melting point, and now that solid turns into a liquid. And if you continue to add energy to the point where these particles experience negligible intermolecular forces, then we've reached the boiling point, and that's where the liquid turns into the gas phase. So these points here, the melting point and boiling points, are different between different substances. Now these are physical change. These are physical phase changes. We're not undergoing chemical changes here. All right. But the melting point and boiling points are different for different substances because they have different intermolecular forces. You can say the melting and boiling points are largely determined by the intermolecular forces found in that substance. Now, I want you to consider three substances: chlorine, bromine, and iodine. These are three halogens, diatomic molecules in the same group. In the chlorine molecule, you have a chlorine atom sharing a pair of electrons with another chlorine atom. We call that a covalent bond. This covalent bond is completely nonpolar. It is purely covalent. There's no difference in electronegativity because they're both chlorines. And you can say that about bromine, iodine, any diatomic molecule. And it doesn't have to be diatomic. There's many nonpolar examples of nonpolar molecules. So how can three completely nonpolar molecules be a solid at room temperature? That's iodine. And bromine is a liquid at room temperature, and chlorine is a gas at room temperature. There must be significant intermolecular forces for iodine to be a solid, bromine to be a liquid, much more so than chlorine, which is a gas. And so what all molecules and atoms have are what's called London dispersion forces. And pound for pound, these are the weakest intermolecular forces. They're just momentary or temporary uneven distributions of electrons. So at any given moment, one side of this molecule can have a slight uneven distribution of electrons on one side, and that side will be temporarily negative, and therefore the other side will be temporarily positive. And so this is known as a temporary dipole. For a moment in time, temporarily, it has two charges. Now, at any other moment, the charges could switch. You could have a shift of electrons on another side of the molecule. So this is an example of how even the weakest intermolecular forces can compound and become significant. Because iodine has 53 electrons undergoing London, and chlorine only has 17. So London dispersion forces are largely dependent on the size of the molecule. All molecules, all atoms that have electrons, which is all molecules and all atoms, they experience London dispersion forces. But they are the weakest type, pound for pound. Now, iodine just has so many electrons that it becomes much more significant than in chlorine. And there's molecules way bigger than iodine. All right, but let's stay with this pound for pound analogy. So because we're going to talk about other types of intermolecular forces, I'm just going to try to use a good comparison. I'm going to use fluorine here as my representative of London dispersion forces. Now, the next type of intermolecular force is your dipole-dipole, and this happens between polar molecules. And the example I use here is hydrogen chloride. Hydrogen chlorine sharing a pair of electrons shares unequally because chlorine is more electronegative. That side is going to have a permanent negative charge, partially negative, and the hydrogen side is going to have a permanent partially positive side. So this is called a permanent dipole. Right? The negative side never goes over to the hydrogen, it's just always stuck on that more electronegative side. So you can look this up. In fact, I'm going to look it up. What do you expect to have the higher boiling point? Hydrogen chloride or fluorine? So I just quickly did a Google search, and you can see the fluorine molecule has a much lower boiling point than the hydrogen chloride. Next up is a specific and stronger type of dipole-dipole interaction known as hydrogen bonds. And these occur when you have a hydrogen covalently bonded to a very electronegative atom such as fluorine, oxygen, or nitrogen. And the reason these are especially strong dipole-dipole interactions is because the significant electronegativity difference between the hydrogen and either oxygen, fluorine, or nitrogen. And the other factor is hydrogen is such a small atom. It just has one proton and one electron. So if that one electron is hanging out somewhere else, the proton is making that side extra positive. So the example here we'll use is water, H2O. And this is not linear because we learned Vesper, right? Water can form two areas of hydrogen bonding. This here area is partially positive. This is partially positive. This is partially negative. Well, this whole side is 2 times that partially negative. So with other water molecules, it has 2 areas of hydrogen bonding because this here area can form a hydrogen bond with another water molecule's lone pair. So one side of a water molecule can form hydrogen bond interactions with the partially negative side of another water molecule. And so you got another one this way to another water molecule's hydrogen, and it's just a network of hydrogen bonding interactions. And you don't have to look this up. You know the boiling point of water is 100 degrees Celsius. So it takes way more energy to separate the intermolecular forces keeping water molecules together than it does HCl or F2. Now, the more hydrogen bonds areas a molecule has, you can expect the boiling point and melting point to go up. Now, finally, this is not an intermolecular force, but we mentioned ionic bonds as a comparison. These don't compare to the attraction between ionic bonds. They represent the strongest type of attractions between cations and anions. These are completely fully charged particles, and up until this point, these are all IMFs, intermolecular forces. These are all partially something or another. Partial charge is called polar, and London dispersion forces. Now, it's not proper to say ionic compounds have intermolecular forces because they're not made up of molecules. They have this repeating crystal lattice structure. So they don't have molecules, but still, in order to melt an ionic compound, you're going to have enough energy to overcome these really strong interactions. Hence, we say ionic compounds typically have high melting and high boiling points. And many ionic compounds, like table salt, has a melting point. This is melting point. These are all boiling points. We're just talking about getting into the liquid stage. All right, melting point of 800 Celsius. Right, and then ionic compounds with even greater lattice energies can be in the thousands. All right, so again, ionic compounds we mentioned just as a reference. And so these are your intermolecular forces and ionic bonds as well. And they all play a large role in determining the melting point and the boiling point of substances.